Hello and welcome back to another VMK in the game development series. In this VMK we're going to finally wrap up all the work we've been doing with the Caligari files. You'll remember in the previous VMK we were able to render objects to the screen, but we left some code out when we were doing the development of the renderer. To start off, I'm going to go into Paint Pro and show you what it is that we're going to try to achieve in this video. Our renderer right now goes and calculates all of the normals per face for all the geometry that gets loaded in from the Caligari file. So for instance, if we had some sort of mesh geometry like so, it will be broken up into triangles because we specified we need to have everything triangulated. And when we go and calculate the normals, what we're doing is we're basically taking each of these faces, so this could be like face 1, this could be face 2, face 3, and so on. Each of these faces will have indices which indicate the values of these vertices. So the indices tell us, okay, this could be, for instance, vertex number 10, this could be vertex number 5, this could be vertex number 6, whatever. Each of them have different numbers. And when we take a look at these indices inside of the code, we can extract the x, y, z coordinates of each of these vertices. We took these vertex values, calculated two vectors, so for instance maybe this vector here from 6 to 10 and then another vector from 6 to 5. We crossed them and we got a perpendicular vector which we called the normal. Basically all of the normals will be perpendicular to the face of each of these triangles, but I'm just going to draw them a little bit off skewed so that you can see them. So if this was perpendicular to this face, we then said, okay, this normal is going to be applied for this face so that when we render this guy, we use the same normal for all three vertices. Now what we want to do is come up with an algorithm so that we can average these normals and give a smooth surface. Because right now, for instance, if we were to render this face here, we would have one vector for the normal, and it would be applied to all three vertices. But then when we calculate the normal for this guy, maybe it's pointing this way. So for every vertex that is associated with this face, we have a different vector here for the normals. But now you can notice that at the joints where face 1 and face 2 meet, you have two different normals. And because of that, you get a very sharp edge that appears on the screen. To fix this, we'll have to apply the same algorithm we did before when we created the cylinder class. There, what we did is we said, okay, we have this normal here and then this normal here. We average the two to get something in between, and then the value in between is the value we use whenever we render this face and this face here for this vertex located here. So we need to come up with a way to calculate all of these averages. But before I go and describe how we're going to do that, let me just demonstrate the problem so that you can see exactly how our renderer right now is behaving. In TrueSpace, I took another object out of the library. This time it's sort of this curved lamp that has this green shade on it. I exported it into our game engine, and let's go and run it to see what we get. So here it is. There's that same lampshade, but now notice that all the edges are completely faceted. You can make out all the faces for the makeup of this geometry. Especially when we go on the inside here, you can see it's very blocky, you could say. So what we're going to do in this video is basically smooth out that guy by calculating the smooth normals for all the faces. So to achieve this, what we need to do is we need to go back into our geometry and figure out, okay, for every single vertex, how many different faces are attached to that vertex. Let me take this guy here as an example. This vertex is part of face number 2, face number 3, this face here, and this face here. So really, there are 5 faces that use this vertex here, which means we're going to have 5 different normals that are calculated for each of these faces. What we need to do is basically get all these normals and then average them out for this vertex. We'll need to do this for every single vertex in our geometry because each one will have a different number of faces associated with it. This one here only has 2 faces. This one here has 3 faces, and so on. So we need to come up with a way to store these normals, which we already have, but then we need a way to say, okay, this vertex belongs to which faces, and then this vertex belongs to which faces. So we need to have some sort of grouping structure. Once we know which vertex belongs to which faces, it will be very easy to pull out the normals for each of these faces, average them, and save them into a new structure, which we can then use when rendering smooth objects. So that's the approach we're going to take. If we go back into our code here, to begin, we'll need to go into the calculate normals function inside the polyh class. And you'll remember here we go and calculate the normals per face. These are the ones we're currently using to render. But we now need to add some more code down here in case we will be smoothing the normals out. So let's start off here. Right after we calculate all the normals, we're going to create a variable here called b_needs_smoothing, and we initialize this to false. What we're going to be doing here is determine whether we need to smooth the normals or not. The smoothing operation is a little bit computationally expensive, so if we don't need to do it, it's better to skip over it. We go into a for loop, looking through every single value inside of this structure here, material angles. And this structure here contained all the different materials that we had that are associated with this polyh, but it also recorded all of the angles that the smoothing is going to be using. Now, the smoothing angle basically determines whether we want to smooth something or not. Actually, let me go into here and show you exactly how this is going to work. From the side view, imagine you had 2 faces. This one here, there's a vertex located here, and then another one here. If we were to calculate the normals for this face here, we would get something that looks like so. If we calculated the normal for this face, we'll get something that looks like this. Now, the smoothing angle is basically this angle here, the angle between these 2 normals. If the smoothing angle is set to 180 degrees, this means smooth everything. So in other words, if this angle, theta, is less than our smoothing angle, then we do want to smooth. If theta is greater than the smoothing angle, then we don't want to smooth. So the smoothing angle is used as a control to determine when to smooth objects and when not to. This is helpful whenever you have complex surfaces that you want to have sharp edges on, but you also want to have smooth looking faces. By controlling this angle, I think I've showed you this before inside TrueSpace, you can give a smooth object smoothness or make it sharp depending on the angle here. So we need to be able to go in here, calculate the normals for every face, and then compare to see whether the angle between specific normals matches the smoothing angle. If it's greater than that, then we don't want to do any smoothing with that specific normal. If it's less, we do want to do smoothing. Now, we're going to create a limit so that if we have any angle that's less than 1 degree, we're going to assume that we're not going to apply smoothing to that because 1 degree is relatively small. So we're going to render that as if it's just a faceted face. If the smoothing angle is greater than 1 degree, then we're going to apply the smoothing algorithm. So here we take a look at the specific material angle's angle value. So this is whatever was saved inside of the structure. If this is greater than pi divided by 180, this is equivalent to 1 degree. So if it's greater than 1 degree, then we want to apply smoothing. So we set this variable to true, and then we break out of the for loop. If all of the smoothing angles that we have saved are less than 1 degree, then we're not going to apply smoothing, which means that when we go down here, we're just going to exit out of our calculate normals function and continue on through. So in other words, we're going to just continue rendering everything as if it's just using the face normals. If we do find something that has a smoothing angle greater than 1 degree, then we will have to apply our smoothing algorithm to calculate all the normals for each individual vertex. So that's what we do down here. First thing we do is we create a container that will help us calculate all of the normals. This container here, I've called it vertex faces, and we should go inside of the .h file and actually define what this is. This is actually a two-dimensional vector. It's an std vector of std vectors that contain integers. This container is going to hold all the vertices that are associated with all the different faces. So for every single vertex, that's going to be this first array, is going to hold an integer which is going to contain which face this vertex belongs to. So we're going to create a structure that has all the vertices, and then we'll know exactly which face each vertex belongs to. Let's take a look at how this works. Down in here, we start off by reserving some memory for the first array. So we know how many vertices we have because we have a separate structure for that. So we can just get the size of the number of vertices, reserve that for this structure here, and then we need to go into the second array internally, and for each one we need to create an empty std vector. So we do that here. We create this empty std vector, and then going through this structure for every single one, we basically push back an empty one of these std vectors. Now we have our two-dimensional array ready to be used. To start filling it with data, we go down here into this loop. We go through every single face that we have inside of our container, and for every single one, we need to save this face's number into the appropriate vertex. The vertex number that is associated with every single face is stored inside of this container here. You'll remember that we had a structure where we had 0, 2, and 4 referring to the indices of every single vertex. The indices for every single texture coordinate were at 1, 3, and 5, but we're not worried about those. So for every single index of the vertices, we save the ID number for the face. After going through this loop, we now know exactly how many different faces each vertex belongs to. Now what we need to do is create a new structure. Well, I call it here faces normals. This structure will hold 3 normals per face, or in other words, one individual normal per vertex. To see the definition of this structure, we have to go back into Caligari polyh.h and just scroll up here, and we'll put it down here underneath all the other structures. All we have here is just 3 normals that are stored inside here, normal 1, normal 2, and normal 3. Now we have to go through every single face and calculate all the normals to be stored inside of the structure. The way we do this is we create a variable here called f_angle in radians, and this is going to be the smoothing angle. We need to extract the smoothing angle from our material 1 structure, which was stored basically inside of this container here. Each face uses a different kind of material, or at least it could. So what we need to do is we need to find the specific material that this current face is using. The way we do this is we go through, we get the material number that this face is using, and we go through our structure here that has all the information stored about each of the materials. Once we find the matching material numbers, we then go in and extract the smoothing angle which was stored earlier for us. After we've found the smoothing angle, we can go down here and calculate the normals for normal 1, normal 2, and normal 3, which are part of this new structure we just finished creating. The way we calculate these normals is using a function here called calculate vertex normal. We pass in the normal of this current face that we're working with. This is the normals that were calculated right at the very top whenever we calculated the normals for every face. We pass in the face ID number, we pass in the smoothing angle, and then we also have this third parameter, which is the index for which vertex we're working with. Remember, we had 0, 2, and 4 stored inside of our structure that has all the vertex information. So we're going to be creating this function in a minute, but after we do all of this, all we need to do is save the 3 normals now inside of our container. So we just take this variable and push it onto our structure here that contains all of the normals. So that's what the calculate normals function does. So what we're left to do now is implement this calculate vertex normal function. We'll go into polyh.h and define this function here. So we have calculate vertex normal. We pass in the normal, the ID for this face, the smoothing angle, and the ID for the vertex that we're working with. Then calculate vertex normal, here's the function. I just placed it right underneath the calculate normals function. So this is going to average out all the normals from faces that share this one vertex. We start off by creating a vector here for the smooth normal that we want to return back out of this function. And initially we set it equal to the faces normal that was passed in. Then we check to see if the smoothing angle is less than 1 degree. If it's not less than 1 degree, we don't need to apply any smoothing, so then we'll just return the current value of this vector here, which basically will be the face normal that was passed in. If the smoothing angle is greater than 1 degree, we need to apply some smoothing. To do this, we begin by getting the ID number of the vertex for this specific face. So here we go. We know which face we're working with. That's this value here. And we know which vertex we're working with because that was this value here that was passed into us. So this is the ID number of the vertex that we're working with. First thing we do is we check to see whether this container, which is that two-dimensional vector we just finished creating, and we check to see whether we already have anything stored at this location or not. If there is something stored here, we need to apply some smoothing. If there isn't any value stored inside of the structure, then we just return v3 smooth normal, which is equal to the face's normal here. Now, if there was something stored inside of this container, we need to apply some smoothing. If I scroll down here, you can see the algorithm that I created to do the smoothing for us. First thing we do is we go into a for loop that goes through this entire container, which holds all the faces that this current vertex belongs to. So if we had 5 faces that belong to a specific vertex, each of those face numbers would be stored inside of this container here. First thing inside of this for loop, I extract the face number that's stored at this current location. So you can see here the index is going through every single one of this container, and the first one that I extract is the face number. I check to make sure that the face number is not equal to this face, and this face is the face that we've passed into here. The reason why I need to do this is because down below I do a calculation for smoothing, but I don't want to add my own normal to this calculation because my own normal was already handled appropriately. So when I do find a mismatch here, so I'm working with a face that doesn't belong to myself, then I can extract that specific face's normal using this container here, which stores all the normals for every single face. So then I have this variable which contains the current normal for the specific face that I'm looking at. Then I compare my own normal with this normal here that we just extracted. If the angle between them is less than or equal to the smoothing angle, then I go in here and I apply the smoothing. If it's beyond the smoothing angle, then I skip over it and I continue looking for the next normal that we have stored. So really, what I'm doing here is I'm going through the container, looking for all the normals that belong to a specific vertex, and comparing each of the normals with my own normal. When I find a match in the angles, if I find an angle that's within the smoothing bounds, then I add it to my smoothing normal value here, so that after I finish all of this, I'll then normalize, and then the result is my average normal. So that's the way that the smoothing algorithm works. And then once it's done, we just basically return the v3 smooth normal. One thing I just want to check here is I don't think we have this function here, getAngle, for a vector 3. So we'll need to go in and implement that. Go into Math, vector 3, and I'll just put it right here on the bottom. Doesn't really matter where you put it. So we have getAngle. we pass in a vector, and we're comparing it with ourselves. So the way we get the angle is we use the dot product of two vectors. A dot B is equal to the magnitude of A times the magnitude of B times the cos of the angle. We want to get the angle, so we can take A dot B divided by this value here, and take the arc cos of the result, and now return us the angle. So here we go. I call arc cos of this value here. And this value here is get cosine angle of vector v. So I've wrapped this calculation for this part here into a separate function, because sometimes whenever you're working with vectors, you may not need to get the exact angle. You may be perfectly happy with the cosine of that angle. So to avoid writing 2 times as much code, I've just called this function here, which is located right up above, that calculates this quantity here, A dot B divided by magnitude A times magnitude B. To do that, we just calculate the denominator part first. We calculate the length of ourselves, multiply it by the length of the vector that gets passed into us, check for division by 0. Once we have that, we calculate the dot product of ourselves with this vector and divide it by the denominator. The value itself may have to be corrected due to rounding, so the value could not be greater than 1, so if it is, we just cap it at 1, and it cannot be less than -1, so if it is, we cap it at -1. If you don't add this code here, you may get some runtime problems because of the precision of your CPU. So make sure you add these in here. Once you have the value corrected, then you can just return it here, which we go and then use with the arc cos value here, that then returns the angle between the two vectors. One thing I'm not quite sure about is whether we've implemented the dot product, and it doesn't look like we did, so we need to implement that as well. I'll put the dot product here right above, and it's very easy to calculate. You just take each component, multiply them together, and add them to the next one. So our x value times this vector's x value plus our y value times the vector's y value plus our z value times the vector's z value, and we return that. That's basically the dot product between two vectors. If you're not too familiar with the dot product or the angles between vectors, you can pull out any standard algebra textbook and they'll explain it in detail. Okay, so let's go and just try to compile this, make sure I didn't make any mistakes. Oh, there's something else missing here. We're missing a function called length. Okay, let's go and implement that then. The length of a vector is equal to the square root of each of the components multiplied together and added to all the other components. So x squared plus y squared plus z squared square rooted gives you the length of a vector. Let's try compiling this now. Okay, so that looks okay now. We can go back into here, and we now have this implemented. So we're pretty much done with the calculating of the normals. What we need to do next is actually use these normals that we calculated here. We need to go into scene.cpp and inside load Caligari file. If we're scrolling down past this initial part where we created everything, right into here, we have a function which is part of poly-h that we're using to create the geometry. Here we're passing in the material ID number, the texture ID number, and remember the last parameter here was the smoothing part. And by default we set this to false because we didn't have the normals calculated for us previously. But now that we do have the normals calculated, we need to change this false value to a function call. And what we want to do here is check this current poly-h's smoothing value. So we need to create this new function here called isSmoothing, and then what this is going to do is return true or false depending on whether we want to use smoothing or not. So in here, we create a definition for the function isSmoothed, and we're passing in the material ID number. And then inside of the CPP file, I'll just put it right here at the bottom. all we're doing is checking to see whether the current smoothing angle is greater than 1 degree, which is pi divided by 180. If it is greater than this, then we return true, otherwise we were returning false. Now there's only one other thing we need to do, and that's located up here inside the create geometry OpenGL function. You'll remember we left out some code here if we are smoothing. So if it's smooth, we don't have any code here, and then if it's smooth down here, we don't have any code. We need to fill this in now. So let's start off with the easier case, which is the one where we don't apply textures. So we know we're going to be smooth rendering. Now we need to use vertex normals rather than face normals. We search through all the different faces, looking for the ones that match the current ID number that we're rendering with. So when we do find a match here, then we go and call GL normal 3F 3 times. Each time we're specifying a different normal value for each of the 3 vertices. And the 3 normals we're using have been stored inside of the structure which we finished creating earlier. So we extract normal 3, normal 2, normal 1, and we're just passing in the x, the y, and the z component values. We need to do something very similar up here when we are texturing, but this time we're also passing in the texture coordinates. So again, we're going through looking for the material ID number. When we find a match, we pass in the normals for each vertex as well as the coordinates for the texture coordinate and the vertex coordinate. So here we go, normal 3, normal 2, normal 1, the x, the y, and the z component. Okay, and that's basically it. So now when we go and compile, if I haven't made any mistakes, which I have, we'll need to go and clean these up. Oh, we forgot to define our structure that contains all of these normals which we calculated up above. Let's go and do that down here. So this structure here contains the normals per face, and this new structure contains all of the 3 normals that each face has. Actually, let's take these 2 guys, move it up here. Okay. Now let's go and compile this and build this. And give it a run. And there we go. Now we can see our lamp is much smoother because it's calculating all the normals dynamically and smoothing everything out to give it a nice kind of smooth finish. You notice down here at the base there are sharp edges because the angle between the edge normals and the ones a little bit up above are greater than that smoothing angle. So the normals do not get smoothed there, but they do get smoothed out around the curved sections of the lampshade as well as around the cylindrical part where the pole is defined. So there we go. We're pretty much done now with the Caligari file loader and being able to render everything onto the screen.